The second set of power functions we're going to consider here are those where the exponent is a negative integer. And in this collection, we're going to start with the odd powers because we haven't seen -1 yet. In fact, these are graphs that we have not yet seen in this course, even though we've worked with these functions otherwise. So these are functions of the form f of x equals x to the negative p, or 1 over x to the p, where p is a positive odd number. Our example here is the graph of f of x equals 1 over x. And this graph has some exciting properties that we haven't seen before. First of all, its domain misses just the 1.0, and we can see that by looking at the function itself. We can take any number we like and divide 1 by it, as long as that number is not 0. I could write that domain in interval notation as well, but set builder notation is more helpful in seeing what's really going on. We just missed that 1.0. Now, the inverse of this 1 over x function is just itself, which helps us to notice that the range is also every real number that isn't 0. We can get every real number that isn't 0 by taking the reciprocal of its reciprocal. In general, if we have one of these 1 over x to the p functions, the inverse is just 1 over the corresponding root. But in the special case where p equals 1, there really isn't a 1th root. In the special case where p equals 1, the inverse is just 1 over x. It's easy to see from the graph, but from the formula as well, that again, we have an odd power, we have an odd function. And one interesting thing that we have not seen before that appears in this graph is that we have 2 asymptotes here. We have a horizontal asymptote at y equals 0, and we have a second vertical asymptote at x equals 0. In general, graphs involving rational functions will have both horizontal and vertical asymptotes, and sometimes other more exciting asymptotes, which is something that you'll see more in later courses. When we want to graph one of these, we will use these 2 points as our key points. Those are the points 1, 1, and -1, -1, along with our asymptotes. When we want to draw a graph that has asymptotes, we'll also need to figure out where those go. Even powers are similar, except that when we have an even power, we get that even function property again. So the even powers that are negative are in the form f of x equals x to the negative p, or 1 over x to the p, where p is even. Our example here is 1 over x squared. The domain of this function is, again, every number except 0. But now we notice that these are going to be fractions whose denominators are always positive. In other words, the output of this function can only be a positive number. The range consists of only the positive numbers and not 0. Like the positive even powers, in order to get an inverse here, we need to split the domain. If we restrict the domain to positive numbers, then the inverse is 1 over the pth root. And if we restrict the domain to negative numbers, then the inverse is the opposite of 1 over the pth root. Once again, with this even power, we see an even function. And like the odd negative powers, we have a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0. It may not be immediately obvious looking at this graph that we do in fact have a vertical asymptote at x equals 0. It may not be immediately obvious that that's where these two curves are converging to, but in fact they are. It's just a little bit slow because we're working with 1 over x squared. When we want to graph one of these, we'll use these two key points, 1, 1, and negative 1, 1. Again, along with the asymptotes. Now, we haven't really seen these properties, but as it turns out, really the only new function here is 1 over x. We can get any x to the negative p power by composing 1 over x with x to the positive p. Pretty much all of the properties, especially for example the inverses of these functions, come from examining that composition.